Our planet has faced annihilation more times than you might believe. Earth's history is filled with moments where everything nearly ended, from city-sized asteroids to volcanoes that darkened the sun. This video uncovers 15 specific occasions when the world stood on the edge of total renewal. You will leave with a completely new understanding of how fragile our existence really is, and how these catastrophes, paradoxically, paved the way for life as we know it. We will explore what happens when the oceans rust and the air itself turns to poison. What does it take for life to cling on when the world freezes over entirely? How close did we come to a silent, empty planet? By the end, you will see the ground beneath your feet not as solid and permanent, but as a stage for epic, near-fatal dramas. What single event do you think came closest to erasing our future? Our world began in fire. For hundreds of millions of years after its formation, the young Earth was subjected to a relentless, planet-shaking assault. This was the Late Heavy Bombardment, a period over 4 billion years ago when the inner solar system became a chaotic shooting gallery. Asteroids and comets, some larger than mountains, slammed into our planet with unimaginable force. A single one of these impacts could vaporize an entire ocean and melt the crust, effectively sterilizing the surface. Just as the first fragile stirrings of life might have begun, the clock was reset again and again by this cosmic violence. So what caused this epic onslaught? The leading theory points to the giant planets Jupiter and Saturn beginning a slow dance through the young solar system. As they migrated, their immense gravity stirred up a vast reservoir of icy bodies in the outer reaches, sending a storm of comets and asteroids careening inward. The evidence for this ancient pummeling is written on the face of our moon. Those vast, dark plains you can see on a clear night are lava flows that filled colossal impact basins, scars from this very bombardment. If the airless moon bears such marks, imagine the devastation on the larger, more dynamic Earth. Each impact was a world-ending event, scouring the crust and boiling the nascent seas into steam. Yet, in a profound paradox, this era of utter destruction also carried the seeds of creation. Those same icy comets are thought to have delivered vast quantities of water to our parched planet, filling the basins that would become our oceans. They may have also brought complex organic compounds, the essential building blocks of life, in the fractured, superheated rocks around impact craters, in deep-sea hydrothermal vents safe from the chaos above. The hardiest early microbes could have found a refuge. This is the recurring theme of our planet's story, where total annihilation and new beginnings are inextricably linked. The violence that nearly erased life forever may have, in fact, provided the very materials and conditions for it to finally take hold, setting a dramatic stage for the next, even more profound planetary crisis. That microscopic revolution, however, came with an apocalyptic price tag. As cyanobacteria perfected the art of photosynthesis, they began exhaling a waste product that was pure poison to the ancient world, oxygen. For 2 billion years, life had been a quiet, anaerobic affair, thriving in airless waters. Then, the great oxidation event began, and the planet itself began to rust. The oceans, rich with dissolved iron, reacted with this new, aggressive gas. The seas turned a bloody red as trillions of tons of iron oxide settled to the bottom, layer by layer, forming the beautiful banded iron formations we mine today. But this was only the beginning of the crisis. Oxygen, a potent greenhouse gas, was scrubbed from the atmosphere by this global rusting, and methane, which had kept the planet warm, was broken down. Earth's thermostat failed, the global temperature plummeted, and ice advanced from the poles. It did not stop. the glaciers kept coming, perhaps until the entire planet, from the equator to the poles, was encased in a mile-thick shell of ice. This was Snowball Earth, a world locked in a deep freeze that may have lasted for millions of years. Can you picture it? A perfect white sphere hanging in space, its oceans solid, its life clinging on in the absolute dark beneath the ice or near volcanic hotspots. For the anaerobic life that had ruled the world, this was a double catastrophe. The oxygen itself was a toxic gas, and the ice age that followed was a global prison. It was one of the most extensive mass extinctions in history, wiping out the dominant forms of life to clear the stage. Yet, from this frozen wasteland, a new world was born. The extreme pressure for survival in this harsh environment may have driven the first complex cells, eukaryotes, to evolve, cells that could harness oxygen for immense energy. The very poison that had caused the disaster became the fuel for a more dynamic, active future. This was the ultimate paradox, a biological innovation that nearly sterilized the planet, only to ultimately enable every complex creature that would ever walk, swim, or fly. Life had seized control of the planet's chemistry and nearly ended its own story, setting a dramatic precedent for the next act, where the planet itself would fight back with pure geological fury. That deep freeze was not a single event, but a terrifying cycle of ice and fire. On at least two occasions, around 720 million and 635 million years ago, our planet became a global icebox. Glaciers miles thick smothered the continents, and the oceans froze over, possibly all the way to the equator. The entire Earth would have looked like a brilliant white snowball from space, its surface reflecting nearly all sunlight back into the void, locking the planet into a self-sustaining deep freeze. What could cause such an extreme climate crash? It began with the slow dance of continents. The supercontinent Rodinia was breaking apart, creating vast new coastlines. Rain falling on these fresh volcanic rocks accelerated a process called chemical weathering, which literally pulls carbon dioxide, a crucial greenhouse gas, out of the atmosphere. At the same time, massive volcanic eruptions may have initially spewed sun-blocking aerosols high into the air, casting a cooling shroud over the planet. As the ice sheets grew, they reflected more and more sunlight, creating a runaway cooling effect that plunged the entire world into the cold. Life was pushed to the absolute brink. Any complex organisms that had begun to emerge were almost certainly wiped out. Survival was only possible in tiny, desperate refuges, like near volcanic hotspots on the ocean floor where warm, chemical-rich water seeped from the crust, or in patches of thin ice where enough sunlight could penetrate to sustain microscopic algae. For millions of years, the planet was a silent, frozen tomb. Yet, the very thing that sealed the ice in place also held the key to its destruction. With the oceans locked solid, the normal processes that remove carbon dioxide from the atmosphere, like weathering, ground to a halt. But volcanoes kept erupting, relentlessly pumping carbon dioxide into the stagnant air. For centuries, this gas built up with nowhere to go, creating an incredible atmospheric pressure cooker. Eventually, the greenhouse effect became so powerful that it overwhelmed the planet's reflectivity. The thaw, when it finally came, was likely explosively fast. In a geological blink of an eye, perhaps just a few thousand years, the global ice cover shattered. Temperatures skyrocketed, soaring to tropical levels worldwide. The meltwater flooded the oceans with nutrients that had been scraped from the continents by the grinding ice. This sudden deluge of food into a sun-starved world created a perfect storm for biological innovation. From this cycle of utter devastation emerged the first simple, multicellular life forms of the Ediacaran period. The planet had been sterilized and reborn, its slate wiped clean for a new, more complex experiment in living. This violent reset set the stage for an explosion of diversity so profound it would forever change the character of life on Earth. That new world of gentle, alien pioneers did not last long. After the deep freeze of the Snowball Earth, the seas teemed with the first large, complex organisms, creatures that looked nothing like life today. The rangeomorphs were the rulers of this tranquil world, soft-bodied beings that grew in fractal, leaf-like patterns, some over 2 meters tall. They had no mouths, no guts, no means of movement. They simply stood anchored to the seafloor, passively absorbing nutrients from the water. For tens of millions of years, this was the pinnacle of complexity, a serene and silent garden on the ocean floor. Then, around 541 million years ago, they were gone. The end Ediacaran Extinction wiped the slate almost clean, a mysterious disappearance that happened just before the riot of life known as the Cambrian explosion. What could have ended this peaceful era? The evidence points not to a single asteroid strike or volcanic cataclysm, but to a slow, suffocating change in the oceans themselves. As the continents shifted and climate fluctuated, vast portions of the deep sea may have become starved of oxygen, creating toxic dead zones that crept into the habitats of these fixed, vulnerable organisms. At the same time, the chemistry of the seawater might have shifted, altering the availability of the specific nutrients these strange life forms depended on. You can see this dramatic vanishing act in the fossil beds of Mistaken Point in Newfoundland. The layers of mudstone, once covered in the intricate impressions of countless rangeomorphs, suddenly become barren. The diversity of life plummets. It was a quiet apocalypse, a slow-motion disaster that nearly reset the entire experiment of complex life before it even really began. Yet, this extinction was not an ending so much as a brutal transition. By removing the stable, established life forms, it cleared the ecological space for something entirely new. Into this vacant world emerged animals that were active, mobile, and hungry. They developed mouths, claws, and shells. They began to hunt. The demise of the gentle Ediacaran organisms created an opportunity for an evolutionary arms race, setting the stage for the sudden appearance of almost every major animal group we know today. The planet had tested its first complex life and found it wanting, preparing the ground for a far more dynamic and dangerous world. A world about to be shaken by a geological catastrophe of unimaginable scale. The tranquil gardens of the Ediacaran had been swept away, replaced by the churning, predatory waters of the Ordovician period. For tens of millions of years, life underwent an incredible diversification, filling the oceans with a spectacular array of new forms. Trilobites scuttled across the seafloor in countless varieties, their segmented armor glinting in the sun-dappled shallows. Brachiopods resembling ancient clams filtered nutrients from the water in vast, bustling reefs. This was a golden age for marine life, a world of immense biological richness built entirely beneath the waves. Then, around 443 million years ago, this vibrant world was shattered by a 1-2 punch of climatic chaos. The first blow came from the south. The supercontinent Gondwana had slowly drifted over the South Pole. As snow and ice accumulated on this vast landmass, they reflected more and more sunlight back into space. The planet's thermostat dialed down and a great ice age began. Glaciers miles thick sprawled across the polar continent, locking up enormous volumes of water. Global sea levels plummeted, perhaps by over 300 feet. The shallow, sunlit continental shelves, the very cradle of marine diversity, were drained and left barren. The warm, stable habitats that nurtured the great reefs simply vanished, exposing countless species to freezing temperatures and destruction. This was a slow, grinding extinction by habitat loss. But the worst was yet to come. After millions of years of cold, the climate suddenly flipped. The ice sheets on Gondwana began to collapse, melting at a rapid pace. All that fresh, cold meltwater flooded back into the oceans, forming a stagnant, low-density lid over the saltier, warmer water below. This stratified the seas, preventing oxygen from the surface from mixing into the depths. Vast stretches of the ocean floor became suffocating, oxygen-depleted dead zones, poisoning any life that had survived the initial freeze. The rapid shift from an icehouse to a greenhouse world stressed the remaining ecosystems beyond their breaking point. In the end, nearly 85% of all marine species were wiped out. The trilobite dynasties were decimated, their numbers forever reduced. Countless families of brachiopods, conodonts, and graptolites simply vanished from the fossil record. It was one of the 5 deadliest mass extinctions in Earth's history. Yet, in the wake of this devastation, new opportunities arose. The few survivors, including early, primitive jawless fish, found themselves in a world with far less competition. They radiated out, evolving to fill the empty niches left by the vanished giants. This extinction underscores a terrifying truth about our planet, that climate volatility itself can act as a powerful agent of planetary renewal. The very same forces that built a rich and stable world for millions of years could, with a slight nudge, dismantle it completely. And as life slowly recovered in the seas, the next great challenge was already brewing, one that would for the first time threaten life's boldest new venture, its move onto dry land. But life on land, that fragile new frontier, was about to trigger its own undoing. The Devonian period is often called the Age of Fishes, a time of incredible diversity in the seas. Armored placoderms, some the size of buses, were the apex predators, while the first sharks darted through the waters. On land, a quiet revolution was underway as primitive plants developed deep, complex root systems, creating the very first soils and slowly weaving a green carpet over the barren rock. This botanical breakthrough, however, contained the seeds of a global catastrophe. As these pioneering forests spread, their roots broke down rock with unprecedented efficiency. This intense chemical weathering pulled massive amounts of nutrients from the land, particularly phosphorus, and washed them into the oceans. You can think of it as the planet's first great fertilizer spill, a deluge of nutrients that supercharged the base of the marine food web. Vast, suffocating blooms of algae spread across the sea surface, and when these microscopic organisms died, they sank into the depths. Their decomposition by bacteria consumed the oxygen from the water, creating enormous dead zones on the ocean floor. The seas began to suffocate from the bottom up. In a horrific domino effect, the anoxic conditions allowed sulfur-eating bacteria to thrive, and they began releasing clouds of hydrogen sulfide, a potent poison that rose to the surface, killing life from below and above. This was not a single, swift disaster, but a prolonged, pulsating crisis that dragged on for 20 million years. Each pulse of nutrient runoff would trigger another wave of anoxia, each one choking the life out of the marine world. The victims were the giants of the age. The massive, reef-building stromatoporoid sponges, which had constructed vast underwater structures for millions of years, were utterly wiped out. The great armored placoderms, rulers of the Devonian seas, found their reign abruptly terminated. They were hunted to extinction not by a superior predator, but by an invisible chemical change in their own environment. It was a brutal irony, the very success of life on land nearly strangling life in the sea. This protracted crisis acted as a bizarre evolutionary filter. The slow, repeated environmental stresses favored creatures that were more adaptable and resilient. The heavily armored fish, so dominant in a stable world, were too specialized to survive. But the more agile sharks and the rapidly evolving bony fish, ancestors to most modern fish and eventually to us, managed to squeak through. Their persistence in the face of this biological poison shows how survival often depends on flexibility over brute strength. The late Devonian extinction serves as a profound cautionary tale from the deep past. It demonstrates that a planetary reset does not always require an asteroid from above. Sometimes the most transformative catastrophes are born from within, from life itself altering the planet's fundamental chemistry. And as the seas finally began to recover from this self-inflicted crisis, the ground itself was preparing for a much louder, much more violent outburst. That quiet poison from the land was nothing compared to the fire that was about to speak. Deep beneath what is now Siberia, a geological fury was building, a wound in the planet's crust that would unleash the single greatest catastrophe life has ever known. 252 million years ago, the Earth cracked open. This was not a single volcano, but a series of titanic fissures that vomited forth enough lava to bury the entire United States under 1,000 feet of basalt. For nearly 2 million years, the eruptions continued, a relentless burning that scarred the continent and filled the air with a cocktail of poisonous gases. But the real killer was not the lava itself, it was the carbon dioxide. The volcanoes pumped trillions of tons of this greenhouse gas into the atmosphere, sending global temperatures soaring. The oceans absorbing this carbon dioxide turned sharply acidic, dissolving the shells of countless marine creatures. Then, the warm, stagnant waters began to suffocate, their oxygen depleted, creating vast, toxic dead zones. The cascade of disaster did not stop there. The eruptions also released halogens that ripped apart the ozone layer, allowing deadly ultraviolet radiation to scorch the land. They belched out clouds of sulfur dioxide and toxic metals like mercury and lead, poisoning the soils and the air. On land and in the sea, the entire planetary system was breaking down. This was the Great Dying, the Permian-Triassic Extinction. In the fossil beds of Meiocean China, the story is written in stark, terrifying layers. One moment, the rock is teeming with the fossils of a vibrant world, with intricate ammonoids, robust brachiopods, and strange, early reptiles. Then, in a geological instant, there is nothing but a thin, gray line of barren clay, a silent tombstone for an entire planet. When the cataclysm finally subsided, over 90% of all marine species and 70% of land vertebrates had been utterly erased. It was the closest life ever came to being completely snuffed out. The world that emerged from this inferno was a ghost town, a hollowed-out shell. The recovery was agonizingly slow, taking millions of years for ecosystems to rebuild from a handful of survivors. Yet, from this near-total annihilation, a new world was forged. The ecological vacuum left by the Great Dying created an unprecedented opportunity. The few hardy reptiles that survived began to diversify, their lineages branching out to fill every empty niche. From their ranks would eventually arise both the dinosaurs and the first, tiny, shrew-like mammals. The planet's most severe crisis had performed the ultimate reset, clearing the stage for entirely new actors. It was a stark demonstration that the ground beneath our feet is not solid, but rests atop a reservoir of unimaginable power, a power that could be unleashed again. But sometimes the end does not come from below. It falls from the sky in a flash of light that outshines the sun. The world rebuilt itself from the ashes of the Great Dying, but its newfound stability was an illusion. For 50 million years, the Triassic period was a laboratory of life. a world where crocodile-like archosaurs patrolled riverbanks and the very first small dinosaurs scurried in the shadows of larger reptiles. It was a fragile, balanced ecosystem, a tentative recovery from the brink. Then, 201 million years ago, the planet convulsed once more. The supercontinent Pangaea began to tear itself in half, and as the land ripped apart, the Earth bled fire. A colossal volcanic region known as the Central Atlantic Magmatic Province erupted, flooding an area larger than continental Europe with lava and saturating the atmosphere with carbon dioxide and sulfur dioxide. This volcanic outburst triggered a rapid and brutal 1-2 punch for the global climate. First, the sulfur aerosols likely caused a short, sharp period of global cooling, a volcanic winter that would have devastated plant life. Then, as those particles settled, the immense volume of carbon dioxide took over, sending temperatures soaring in a runaway greenhouse effect. The oceans turned sharply acidic, dissolving the shells of marine creatures and unraveling the food webs that supported life in the seas. On land, the delicate balance was shattered. The large, slow-moving amphibians and many of the dominant reptile groups, which had thrived in the stable Triassic world, could not adapt to the sudden, violent shifts. Their reign ended not with a bang, but with a prolonged, poisonous gasp. The fossil record from this time shows a dramatic turnover. In places like the Newark Basin in eastern North America, sedimentary layers tell a clear story. The diverse fossil assemblages of the late Triassic suddenly give way to a much poorer, less varied collection of species. It was a classic bottleneck event, an evolutionary filter that tested every lineage. The winners in this deadly contest were the dinosaurs. Their upright posture, more efficient respiratory systems, and potentially even their insulating feathers may have given them the critical edge to survive the wild temperature swings and the periods of food scarcity. With their main competitors gone, the world was suddenly, overwhelmingly, theirs for the taking. This extinction did not just clear the stage, it handed the leading roles to a specific cast of characters. The dinosaurs exploded in size and diversity, embarking on a 135 million year domination of the planet. The Triassic-Jurassic event is a stark lesson in planetary cycles, a reminder that even recovery is temporary. Just as life had filled one vacuum, another catastrophe arrived to create a new one, paving the way for the Age of Giants and setting a dramatic precedent for the most famous cosmic intervention of all time. The reign of the dinosaurs ended in a single day. For 135 million years, they had been the undisputed masters of the planet, from the towering sauropods that shook the ground to the razor-toothed theropods that ruled the food chain. Then, 66 million years ago, a mountain of rock and metal, 10 kilometers wide, screamed through the atmosphere and slammed into the shallow seas near what is now Chicxulub, Mexico. The energy released was beyond comprehension, equivalent to billions of the nuclear bombs created by humanity. The immediate effects were apocalyptic. The impact vaporized rock, creating a fireball that incinerated everything within hundreds of miles. Colossal tsunamis, taller than any in recorded history, radiated out from the crater, scouring coastlines across the globe. The shockwave triggered earthquakes of unimaginable magnitude, and superheated debris raining back through the atmosphere ignited a worldwide firestorm, turning entire continents into a blazing inferno. But the real planet-killing blow was more insidious. The impact lofted trillions of tons of dust, soot, and sulfate aerosols high into the stratosphere, creating a perpetual sun-blocking shroud. The world was plunged into an impact winter. Sunlight vanished for months, perhaps years. With photosynthesis crippled, the base of the food chain collapsed. Plants died, then the herbivores that ate them, and finally the great carnivores that ruled them all. In the oceans, the same darkness starved the phytoplankton, causing a cascade of extinction that wiped out the magnificent marine reptiles and the intricate ammonites. The evidence for this cataclysm is written in a thin, global line of clay. This is the KPG boundary, a layer rich in the rare element iridium, which is abundant in asteroids but scarce on Earth's surface. It is the planet's indelible scar, a fingerprint of the impact that separates the age of dinosaurs from the age of mammals. This event was the ultimate demonstration of cosmic randomness, a lottery of destruction where the wrong rock in the wrong place dictated the future of life. The non-avian dinosaurs, perfectly adapted to their stable world, were utterly unprepared for this and perished almost to the last. Yet, in the darkened, devastated world they left behind, a handful of survivors clung to life. Small, burrowing mammals, nocturnal and omnivorous, had the traits needed to endure the long winter. They emerged from the shadows into a world emptied of its giants, finding a planet of vacant niches ripe for the taking. From these humble survivors would eventually spring the entire radiation of mammals, including the lineage that would one day lead to us. The asteroid did not just end an era, it handpicked the next inheritors of the Earth, proving that the ultimate agent of planetary renewal can fall from a silent, indifferent sky. The world the mammals inherited was not a stable sanctuary. Just 10 million years after the dinosaurs vanished, the planet experienced another violent fever. 56 million years ago, a colossal and rapid release of carbon dioxide and methane erupted into the atmosphere, an event known as the Paleocene-Eocene thermal maximum. The source of this greenhouse explosion remains a subject of intense debate, perhaps triggered by massive volcanic activity in the North Atlantic or by the sudden destabilization of frozen methane deposits on the seafloor. Regardless of the cause, the effect was swift and severe. Global temperatures rocketed upward by 5 to 8 degrees Celsius in a geological heartbeat, a change that unfolded over just a few thousand years. The oceans, absorbing this sudden influx of carbon dioxide, turned sharply acidic. In the deep sea, where conditions are normally constant, the change was catastrophic. Entire communities of single-celled organisms called foraminifera saw their shells dissolve in the corrosive waters, leading to a wave of extinctions on the ocean floor. The warmer, less dense surface water also stratified the seas, slowing the global conveyor belt of currents and creating vast, oxygen-poor dead zones. On land, the world became almost unrecognizable. Lush, tropical rainforests stretched all the way to the poles, with alligators and palm trees thriving in the Arctic. This wasn't a gentle warming, it was a planetary upheaval that forced life to migrate, adapt, or die. And in this climate crucible, evolution was accelerated. As forests expanded and new niches opened, mammals underwent a dramatic transformation. It was during this thermal maximum that we see the first unmistakable ancestors of modern hoofed animals, the artiodactyls, appear in the fossil record. More significantly for our own story, this is the period when the earliest primates, small and nimble, began to spread through the canopy. The heat and the changing plant life pressured these creatures to develop new diets, new forms of locomotion, and sharper senses. The petum stands as one of the best natural experiments for understanding our current climate crisis. It demonstrates with terrifying clarity how a rapid injection of greenhouse gases can force the entire Earth system into a new, volatile state, reshaping oceans and driving biological change at a breakneck pace. It nearly reset the world once again, but in doing so, it forged the lineages that would lead to deer, cattle, and ultimately to us. This deep time lesson in climate volatility reveals that the planet's thermostat is not just a dial, but a switch that can flip, setting the stage for the next great chill that would soon grip the world. That tropical hothouse could not last. The planet's long summer was drawing to a close. Around 34 million years ago, a profound chill settled over the Earth, marking the transition from the Eocene to the Oligocene epoch. This was not a sudden impact winter, but a slow, inexorable shift driven by the planet's own machinery. The primary culprit was a dramatic, long-term drop in atmospheric carbon dioxide. As levels of this key greenhouse gas dwindled, the planet's ability to retain heat weakened, and global temperatures began a steady decline. But the cooling was supercharged by a monumental geological event, the final separation of South America from Antarctica. This tectonic divorce opened a deep, cold ocean channel around the South Pole, the forerunner of the Antarctic Circumpolar Current. This relentless, circling current isolated Antarctica from warmer equatorial waters, allowing it to transform into a frozen continent for the very first time. Vast ice sheets began to creep across the land, locking up enormous volumes of water and causing global sea levels to plummet. The world was becoming colder, drier, and far more seasonal. For the lush tropical ecosystems that had stretched from pole to pole, this was a death sentence. The great global greenhouse was shattering into distinct climate zones. The evidence of this great cooling is captured in the microscopic fossils of the deep sea. The shells of tiny foraminifera show a distinct chemical shift, a permanent step down in global temperature recorded in the ocean mud. On land, the change was even more dramatic. Vast, humid forests shrank back toward the equator, replaced by more open woodlands and, for the first time, expansive grasslands. This shift in the landscape was a brutal filter for the planet's life. The archaic mammal groups that had thrived in the warm, uniform world of the Eocene found themselves struggling. Many early, primitive forms of hoofed mammals and carnivores simply could not cope with the cooler temperatures, the drier conditions, or the new, tougher vegetation. They faded away, their lineages ending in a slow-motion extinction. But nature abhors a vacuum. As the forests receded, new opportunities opened up. On the newly isolated continents of South America and Africa, evolution began to experiment in spectacular isolation. In the expanding grasslands, speed and stamina became more valuable than brute strength for ambush predators. A new type of predator emerged, one with long, slender legs built for running down prey on the open plains. These were the first true dogs and cats, ancestors of the wolves and big cats we know today. The Eocene-Oligocene transition demonstrates that a planetary reset does not always require a fiery cataclysm. Sometimes the most profound changes come from a slow, creeping chill, a gradual alteration of the global thermostat that selectively prunes the tree of life. It forged a world that was recognizably modern, a world of ice caps and grasslands, of swift predators and grazing herds, a world being perfectly prepared for the coming age of ice. That creeping chill did not relent. 14 million years ago, the planet entered a new phase of cooling, the Middle Miocene disruption. This was not a sudden catastrophe, but a slow, grinding transformation driven by the slow-motion collision of continents. As the Indian subcontinent continued its relentless push into Asia, the Himalayas soared ever higher. Simultaneously, the Andes Mountains were rising in South America. These new, immense mountain ranges exposed vast expanses of fresh, unweathered rock to the atmosphere. Rain, falling on these steep slopes, accelerated a process called silicate weathering, a natural chemical reaction that pulls carbon dioxide directly out of the air. Planet's primary greenhouse gas was being steadily scrubbed from the atmosphere, and Earth's thermostat was dialed down yet again. The global cooling intensified, and the ice sheets on Antarctica grew thicker and more permanent. This climatic shift had a profound effect on the world's plant life. Lush, dense forests which had dominated the mid-latitudes for millions of years began to retreat. In their place, a new kind of ecosystem exploded across the continents, the grasslands. Vast, open savannas stretched from North America to Eurasia and Africa, a sea of wind-rippled grass under an expanding sky. For the animals of the time, this was an existential crisis. The world was literally changing beneath their feet. Large, leaf-eating mammals known as browsers, creatures like the bizarre chalicothers with their horse-like heads and clawed feet, found their forest homes fragmenting. Their specialized diet of soft leaves became a liability as their preferred food sources vanished. Many of these magnificent, specialized giants could not adapt and were driven to extinction. It was a brutal, continent-wide filter that favored a new kind of survivor. As forests gave way to grasslands, toughness became the key to survival. Plants like grasses, fighting to survive in harsher, drier conditions, began incorporating tiny particles of silica into their stems and leaves, essentially growing blades of glass. This was a devastating defense mechanism against hungry mouths. In response, a new wave of mammals evolved. Grazers like the early horses, hypsodonts, developed incredibly high-crowned teeth that could withstand a lifetime of chewing on this abrasive food. Their legs grew longer for swift escapes across open plains, and their digestive systems adapted to break down the tough cellulose. This was also the era when the ancestors of modern elephants began their dramatic diversification, their trunks and tusks becoming tools for a life spent manipulating a changing world. The disruption even reached the oceans. The cooling and increased ice volume altered global ocean circulation, shifting nutrient upwellings and changing the habitats for countless marine species. The fossil record from places like the Great Plains of North America tells this story clearly. One layer shows a world of forest-dwelling creatures. The next reveals a new cast of characters built for speed and endurance on the open ground. This event demonstrates that the most powerful forces reshaping our planet are often the slowest. Mountain ranges growing over millions of years can alter the very chemistry of the air, which in turn rewrites the destiny of every living thing. The Middle Miocene disruption did not just cause extinctions, it engineered a new world, a world of grass and grazers, a world being perfectly prepared for the coming ice ages. That slow cooling culminated in a world of ice and giants. The Pleistocene epoch was the age of the Megafauna, a time when the northern continents were roamed by woolly mammoths with tusks like curved tree trunks, saber-toothed cats with dagger-like fangs, and ground sloths so massive they could shake fruit from tall trees. This was a spectacular menagerie of colossal creatures, perfectly adapted to the cold, grassy steppes that stretched from Europe to North America. Then, with shocking speed, it was over. Around 11,700 years ago, as the last great ice sheets retreated, a wave of extinctions swept across the globe. In the geological blink of an eye, most of these magnificent giants vanished forever. What could have caused such a rapid, continent-wide collapse of the largest animals on Earth? The evidence points to a deadly synergy, a perfect storm of two powerful forces. The first was a natural climate shift. The world was warming, and the vast, dry mammoth steppes were transforming into wetter tundra and forests, habitats that were less suitable for the specialized grazers. But climate change alone does not explain the abruptness of the disappearances, which closely track the arrival of a new and highly efficient predator on these continents, humans. Armed with sophisticated stone-tipped spears and cooperative hunting strategies, Homo sapiens moved into new territories and encountered animals that had never learned to fear them. The fossil record is stark. In North America, the archaeological sites of the Clovis culture are often found alongside the bones of mammoths, showing clear evidence of butchery. In Australia, the timeline is even more striking. The continent's unique megafauna, including a 2-ton wombat-like diprotodon and a massive predatory lizard, disappeared shortly after humans first set foot on the shore around 45,000 years ago. It was not necessarily a blitzkrieg of overhunting, but a death by 1,000 cuts. These large animals reproduced slowly, and even a modest amount of hunting pressure on key populations could have pushed them past a tipping point, especially as their habitats were simultaneously changing. The loss of these giants was not just a tragedy of vanished species, it was an ecological catastrophe that reshaped the planet itself. Without mammoths and other large grazers to knock down trees and fertilize the soil, the mammoth steppe fragmented. Vegetation patterns changed and fire regimes intensified, altering entire landscapes. The age of giants had ended, not with a geological cataclysm, but with the quiet, persistent influence of a single, clever species. This event marks a profound turning point in Earth's history, the moment when a planetary renewal was no longer driven solely by asteroid impacts or volcanic fury, but by the actions of humanity itself, setting a precedent for the crises still to come. That sudden chill was a ghost from the past. Just as the last ice age seemed to be releasing its grip, the world was thrown back into the deep freeze. Around 12,800 years ago, at the dawn of human civilization, the seasons reversed. For over 1,000 years, glaciers began to advance once more, and a bitter cold settled over the northern hemisphere. This period is known as the Younger Dryas, and its cause remains one of the most tantalizing mysteries in Earth's recent history. The leading and highly controversial explanation is a cosmic one. The Younger Dryas impact hypothesis proposes that a comet or asteroid, perhaps a full kilometer wide, fragmented in the atmosphere and exploded in a series of airbursts over North America. The force would have been millions of times more powerful than the atomic bomb dropped on Hiroshima, instantly igniting wildfires that scorched an entire continent. The evidence for this cataclysm is buried in a thin, dark layer of sediment. Researchers have found concentrations of nanodiamonds, microscopic diamonds formed under immense pressure and heat, alongside tiny spheres of melted rock and soot from continent-wide fires. This layer sits exactly at the moment the climate flipped, a celestial fingerprint at the scene of the crime. The consequences were swift and devastating. The soot and dust from the impact and fires would have shrouded the atmosphere, blocking sunlight and plunging the planet into a rapid cooling event. This sudden climate shock was the final blow for the Pleistocene megafauna. Creatures like the mammoth and the mastodon, already stressed by a warming world and human hunters, now faced a collapsed ecosystem. Their food sources vanished under the cold, and they disappeared forever. The impact also struck at the very heart of human progress. The Clovis people, sophisticated big game hunters whose distinctive stone spear points are found across North America, saw their world evaporate. The herds they depended on were gone, and their complex culture, one of the first and most widespread in the Americas, collapsed and vanished from the archaeological record. It was a near-total reset for human society on the continent, setting back the development of civilizations for centuries. While many scientists debate the evidence, the power of this hypothesis lies in its stark warning. It suggests that even a relatively small cosmic event, a fragmenting comet, can have an outsized effect capable of derailing global climate and halting the march of human history. The Younger Dryas event reminds us that planetary renewals are not confined to the deep past. They can happen in a geological instant, even within the span of human memory, forcing us to look up and consider what other near misses might be written in the ice and rock, and more importantly, what threats still loom silently in the darkness above. That cosmic impact was a stark reminder of our vulnerability, but the next threat emerged from the planet's own fiery heart. Roughly 74,000 years ago, a titan stirred on the island of Sumatra. Mount Toba did not simply erupt, it tore itself apart in a supereruption so colossal, it makes all historical volcanic events look like gentle puffs of smoke. It ejected nearly 3,000 cubic kilometers of rock, ash, and dense gas into the upper atmosphere, enough to bury the entire state of California under 20 feet of debris. The immediate aftermath plunged the world into a volcanic winter that may have lasted for a decade. Sunlight was filtered through a global shroud of sulfur aerosols, casting a dim, hazy pall over the planet and sending average temperatures plummeting by as much as 10 degrees Celsius. For the small, scattered bands of early humans, this was an existential crisis. Their world, already challenging, became a frozen, sunless landscape where food chains collapsed. Genetic studies of modern human populations reveal a startling clue, a severe bottleneck in our ancestry that dates to this exact period. The evidence suggests the total human population may have crashed to as few as 1,000 to 10,000 breeding individuals. Our entire species was pushed to the very brink of extinction, clinging to survival in isolated refuges, perhaps in coastal Africa or other sheltered pockets. This was not just a population collapse, it was a dramatic evolutionary filter. In these small, intensely pressured groups, cooperation, communication, and the ability to innovate became matters of life and death. The social and intellectual traits that allowed these groups to share scarce resources, plan for the long term, and adapt their tools to a radically changed environment were powerfully selected for. The Toba catastrophe may have inadvertently forged a smarter, more resilient, and more socially complex human. The world that eventually emerged from the long winter was different. With so much competition removed, these newly robust human populations began to expand and migrate with renewed vigor, their refined skills allowing them to colonize new lands across the globe. The supereruption nearly erased us, but in doing so, it may have accelerated the very cognitive and cultural developments that would eventually allow humanity to become a planetary force in its own right. This event marks a profound shift in the story of planetary renewal. For the first time, the agent of change was not just an external force, but a thinking, adaptable survivor whose resilience would soon allow it to shape the world for better or for worse. These cycles of fire and ice are not random misfortunes. They are part of a grand, dynamic pattern written into the very fabric of our planet. To truly grasp the scale of these 15 near resets, we need to step back and see the entire stage on which this drama unfolds. The geological time scale, from the fiery Hadean to the human-influenced Anthropocene, reveals a rhythm of long, stable periods punctuated by sudden, catastrophic upheavals. This concept, known as punctuated equilibrium, tells us that evolution is not a slow, steady crawl. It is a story of calm interludes shattered by brief, violent revolutions that force life to adapt or perish. The engine driving much of this change is the slow, relentless dance of plate tectonics. Continents collide and mountains rise, altering wind patterns and ocean currents, which in turn can plunge the world into an ice age or transform it into a hothouse. These geological shifts set the stage, but the final act is often a complex interplay of Earth systems. A volcanic eruption, for instance, is not just a local event. It pumps gases into the atmosphere, which alters the climate, which then acidifies the oceans, creating a cascade of feedback loops that can amplify a crisis into a global catastrophe. So how do we know all of this? The evidence is locked away in natural archives. Ice cores drilled from ancient glaciers contain tiny bubbles of fossil air, a direct sample of the atmosphere from hundreds of thousands of years ago. The fossil record is a library of past life, where sudden changes in the types of species found in rock layers mark the precise moment of a mass extinction. And isotopic data, the chemical fingerprints within rocks and shells, can tell us the temperature of an ancient ocean or the acidity of a long-vanished sea. By piecing together these clues, scientists reconstruct these epic episodes not as isolated disasters, but as interconnected chapters in a single, continuous story. This context transforms our countdown from a simple list of catastrophes into a profound exploration of planetary resilience. Each renewal, no matter how devastating, forced innovation. Each extinction cleared space for new experiments in life. The ground we walk on, the air we breathe, and the life that surrounds us are all products of this relentless cycle of destruction and rebirth. Understanding this deep pattern does more than satisfy our curiosity about the past. It gives us a new lens through which to view our own moment in Earth's history, a moment where the forces of renewal are once again stirring. Our journey through deep time reveals a planet in constant, violent conversation with itself. From the cosmic bombardment of its infancy to the volcanic winters that nearly erased humanity, Earth has faced down annihilation time and again. This is not a story of random disasters, but a recurring cycle where destruction and rebirth are two sides of the same coin. Each crisis, no matter how devastating, forced life to innovate. The poison of oxygen paved the way for complex cells. The deep freeze of a snowball Earth cleared the stage for the first multicellular organisms. The asteroid that ended the dinosaurs handed the world to the mammals. Our very existence is a product of these near-total resets, a testament to life's stubborn refusal to surrender. This grand tapestry of destruction and renewal forces us to look at our own world with new eyes. The same forces that shaped our past are still at work today, but now a new element has entered the equation. Human activity, from the clearing of continents to the altering of the atmosphere, echoes the power of those ancient volcanic provinces and asteroid impacts. We have become a geological force capable of triggering changes on a planetary scale. This is not a reason for despair, but a profound call to responsibility. Understanding the fragility and resilience woven into our planet's history gives us a unique opportunity. We are the first species with the capacity to foresee the consequences of our actions and the power to choose a different path. We can learn from the deep past to protect the future, to ensure that the next great renewal is not one we inadvertently cause. Let this journey inspire a deeper appreciation for our shared planetary heritage and a renewed commitment to safeguarding its delicate, miraculous balance. Which of these 15 near resets do you find most fascinating? Was it the quiet poison of the Devonian or the single day that ended the dinosaurs? Share your thoughts in the comments and subscribe for more explorations into the epic mysteries of our world.